Going to introduce our first keynote speaker, which is David Walter. David Walter is from the Department of Energy, and he is a technology manager for the Systems Integration Team of the Department of Energy Solar Energy Technology Office. He's interested in providing resilience to the grid through the innovative use of distributed energy, as well as developing advanced grid-forming capabilities for inverter-based resources. Prior to joining the Department of Energy, he worked in the insurance industry, providing risk analysis for solar and wind installations, and was a pilot in the deep sea research submarine Albi. David is a registered professional engineer and project management professional, having graduated from the United States Naval Academy with a bachelor in ocean engineering and served in the U.S. Navy. So we would like to welcome David's presentation. So David, the stage is yours.
Thank you very much, Aaron. Good morning, everybody. Thanks for joining this great workshop. I've been working with this team for the last, I guess, 2.5 years now on a project, and it's just been really great to see how everything's come together and getting ready to do demonstrations. So today I'm going to be talking
can you give me 1 second? I want to make sure that you are okay. Now I can see your slides. Sorry.
Oh, okay. Sorry. So yeah, I just wanted to spend some time this morning to introduce who our office is. The Solar Energy Technology Office is part of the Department of Energy, and where we fit in some of the research that we do, and why it's important that not only our office, but the Department of Energy as a whole is really invested in doing research into how can we provide a more resilient grid. So I'll go through some of the research that our office in particular has been performing and our view of what we can do in the future. So who is the Solar Energy Technology Office? So our mission is to advance the deployment of solar technologies, as well as looking at the decarbonized economy goals that the Biden administration has put out from decarbonizing the power sector by 2035 and just decarbonizing the economy in general by 2050. And our path towards doing that is really driving technology innovation to reduce the costs of solar so that solar energy can be affordable and accessible to all Americans, as well as looking at what technologies are needed to make the grid more reliable and resilient, as well as providing security, and looking at different paths for providing manufacturing and job growth within a wide range of applications throughout the U.S. Economy. And where do we sit? Some of you may definitely be familiar with the Department of Energy. The Department of Energy handles quite a number of different tasks. Our office in particular, we sit under the Undersecretary of Energy, who also has the Office of Energy Efficiency and Renewable Energy. So we're one of the key renewable energy offices. We also, though, work with a number of other offices within EERE, and as well as the Office of Electricity and other offices like CSER on cybersecurity for distributed energy resources. My team in particular, though, is the Systems Integration Team, and our focus is on everything basically from the inverter out to the grid. So we are looking at power electronics, we're looking at controls for the distribution grid, as well as how can we utilize inverter-based resources to provide grid services to the grid, as well as the best ways to integrate storage, improve solar forecasting so that grid operators and asset managers can really have a better understanding of not just the annual and day-to-day output of those systems, but really trying to drive down to the minute-level forecasting ability so that grid operators can make sure that their generation is always matching load properly. We also look towards enhancing grid grid codes and what standards are going to be needed to better integrate all these solar technologies onto the grid. So there's a lot of different definitions for what resilience is. The definition that the Department of Energy has come down on is the ability to prepare for and adapt to changing conditions and withstand and recover rapidly from disruptions from deliberate physical or cyber attacks, accidents, and naturally occurring threats and incidents. So our goal is to provide resilience to the entire grid. Our office in particular is a little more focused on the distribution side of the house and looking at different paths for distributed energy resources such as rooftop solar, community solar, storage, electric vehicles. How can we utilize those assets to help the grid maintain itself when there is an event that may take down transmission or certain sectors of the grid? And this has been an important area of study for us and focus because, as I'm sure all of you are well aware, just over the last 20 years, there's been a large number of events that have caused significant impacts to the grid and to the economy in general based on repairs from hurricanes and flooding. Even just in the last couple of years, there's been multiple wildfires and there's currently a heat wave in California, the polar vortex that occurred last year and the year prior to. They have significant impacts on the grid, and by researching what those impacts are and how can we move beyond reliability metrics and ways to just ensure that the hardware is more reliable, how can we group all of these assets together so that when needed in a distribution setting, we can provide grid services while the rest of the grid is coming back up in force. And the Solar Energy and Technology Office, we're definitely not the only part of the Department of Energy that is working on this. We are a member of the Grid Modernization Laboratory Consortium, the GNLC, if you've heard that as an acronym. So working with all of the national labs, all 14 labs, on different ways to support what is needed for resilience in terms of planning and sensing and measurement, as well as understanding what generation and assets are available, and providing institutional support to federal agencies and state regulators so they can understand from like an unbiased third-party view of what the capabilities of not just renewables, but the power sector in general. So looking at how to design a more resilient system, we really need to cover multiple areas. So there's planning that needs to be done before an event occurs. So looking at how can we harden the distribution system, what types of mitigation strategies will you put in place for flooding, looking at making sure that your assets have the right cybersecurity in place, as well as thinking about where will we need to install additional generation assets for when the distribution grid portions of the distribution or the transmission grid may go down. But then as we enter the phase of what happens to the grid during the event, like the performance of the grid will go down as things fail and like lines go down or grid assets are broken. So another key portion is making sure that the correct sensors are in place so that the grid operator can know what is actually happening on the grid. That is a major thing that a lot of distribution operators don't always have a real clear picture of what is occurring on the grid. So, looking into cheaper sensing technology, as well as remotely operated reclosers and fault location, isolation, and restoration processes, doing the right research and commercialization of those packages so that they can be in place before the event happens and then can be used during the restoration phase in order to realign how the grid is powering, especially critical infrastructure, but looking at underserved communities, because as we've seen in like Hurricane Maria in Puerto Rico or some of the events in Texas, some of those underserved communities may go days, weeks, and months before the grid is actually restored. So being able to quickly respond to those events and bring back the power to some of those communities is really important for them to get back to their lives and be able to support themselves moving forward. We also want to be able to learn from any events that have occurred from that, and be able to redesign where necessary and implement new measures so that after that event, after we recover from that event, let's see how we can better restore us, not just back to the resilient state we were before an event occurred, but make ourselves even more resilient and have a higher performance level. So some of the funding opportunities and portfolio of projects that we've done through the years to support this, I'll start with our ASSIST program, the Advanced Systems Integration for Solar Technologies. The project that we're working with University of Utah here came directly out of this funding opportunity. So you'll hear a little bit more about some of the projects that were part of this. But it's really had a focus on providing situational awareness to the grid operator so that they can understand what is actually going on the grid. So investigating outages, either from cyber attacks or physical occurrences, and then looking at different ways to provide resiliency to the grid by either reconfiguring how the distribution system is set up, or at least being able to understand or identify and understand what the critical infrastructure needs are so that power can be rerouted so that, like, hospitals and fire stations, an example, can be repowered. Another group of projects that we have working on this are being able to look at the distribution grid and provide a coordinated community microgrid to enable that the entire community is best served as well as it can. So, the grid is set up and a grid operator operates in the most efficient manner they can. But if, let's say, a fault occurs, like here in the middle of this, how can we reroute the system by understanding what the power flows need to be and what the most critical loads are, so prioritizing who needs power and when, so that we can reorganize basically where that power goes. One of the projects that we have working this is run out of the National Renewable Energy Laboratory, where they're really trying to examine the grid, a grid area as a whole, and breaking it up into individual cells, so that during normal operations, everything operates as it has normally. But when an event occurs, we can break up the distribution system into these basically like microcells, which are like the smallest unit we can get, where there's enough generation to serve a load, and be able to control the assets as best as we can within that cell, as well as being able to provide means for cells to interconnect with each other when faults are cleared, or being able to request from each other if they need additional generation, or if there's loads that are underserved in neighboring cells. So through this project, they're in the middle of completing some modeling work, and we'll be doing some demonstrations in Colorado where they're also be deploying mobile energy storage units, like in a pre-event type of scenario where if they feel an event is going to occur, bolstering some of those cells in areas where they may not have enough generation. Another aspect of preparing for a resilient event, and as I mentioned in the ASSIST program, looking at situational awareness, but another key need for better communications and sensing technologies is to provide not just control of loads and generation, but also understanding what the state of the grid is so that adaptive protection can be provided. So the distribution grid is set up with historically power going from the transmission system down to the load. So the protection scheme is set up with relays understanding where the loads are going to be, as well as utilizing traditional generation, which can provide a large amount of fault current. Well, utilizing inverter-based resources and two-way power flow through the distribution network, we need to be able to quickly adapt those relays and relay settings so that the grid can understand, all right, now I know where the power is now coming from, and being able to quickly decipher small faults because those relays may not be seeing large fault currents flowing through them anymore. So we have a number of projects, this one being led out of Sandia National Lab, that is looking at real-time monitoring and short circuit studies that are being done out on the grid edge so that those relays can understand what the state of the grid is, and then being able to adjust the settings appropriately for when there's more generation from the distribution side than from the transmission side. Another part to adding to this is the utilization of smart inverters and power electronics. So smart inverters have been around for a number of years now. There's a number of standards that are out there. Most recently, IEEE 1547 has been re-released with new requirements, but being able to utilize some of the inverter functions that are built into these inverters and that are part of these standards will allow utilities to better use them as monitoring devices, as well as being able to look at what types of grid services may be needed to increase the flexibility of the grid. So by expanding the types of services that are available and utilized from those smart inverters, we'll be able to provide voltage and frequency support, looking at how the demand response and what the demands are and the load forecasting will be, so that if we can interface with a smart inverter or a smart meter, we can then bridge down another level to controllable loads so that we can potentially provide even better demand response than traditional systems, which may or may not have like a relay on an HVAC system or connections aggregated through a smart thermostat setup. We're looking to being able to interface with even more smart loads. But it also allows us to have a more holistic look at what the capabilities of the grid are and what the needs are, so that there can be better use of the transmission system, as well as maybe looking at what non-wires alternatives can be to provide additional hosting capacity to the distribution system and be able to fit more distributed assets on board. One project that we had, this is actually from 2017, but demonstrating grid services from smart inverters was with a utility scale system that the National Renewable Energy Lab worked with CAISO and First Solar to demonstrate by having some headroom, they were able to operate this solar plant with no storage as if it was a traditional generator, being able to provide for fluctuations in voltage and frequency. And we have additional projects that are working more to integrate storage with that, as well as being able to understand more what the grid services are needed by distribution and utility managers. And as I mentioned, like looking at ways to increase the hosting capacity in distribution grids, we're looking towards how to integrate and control power systems with more and more inverter-based resources, such as wind, solar, storage, fuel cells. So there's a number of small islanded grids and even some larger islanded grids that are seeing upwards of 60 to 70%, even 100% on the really small grids penetration. So some of those grids are servicing all of their loads using inverter-based resources. But it gets extremely complicated when we're looking at larger areas and larger interconnected grids. And one of the areas of research that our office in particular has been highly focused on is in the grid form, developing better methods to model grid forming controls, as well as understanding how those controls will interact with each other. So we've formed the UNIFI Consortium, which is co-led by National Renewable Energy Laboratory, the University of Texas Austin, and EPRI. This is a consortium that has a number of participants from industry, from utilities, from academia, and they're looking at research and development for, like I said, the modeling and controls. How do we better integrate grid forming controls into hardware? So understanding what the fault current needs will be, and then demonstrating these on a small scale, being able for inverter manufacturers to test these systems on like a 1 megawatt scale, as well as putting in a 20 megawatt demonstration so that we can show how a large number of grid forming inverter-based generation assets can work together to support a large grid, which is extremely important for resilience. So as mentioned before, when if we lose the transmission system or certain parts of the distribution grid, we need to be able to provide that frequency support, and grid forming inverters are really there for that. There's also an aspect of outreach and training as part of this, so that we can provide education for the next generation grid operator and grid designers, as well as workforce development for current industry, so that they can understand what the changes that are coming will be. And our most recent funding opportunity, which we're actually in the middle of reviewing, is the Renewables Advancing Community Energy Resilience, RACER. So as I mentioned back in the beginning, on the planning side of resilience, it's extremely important to understand what the community needs are. So we've requested proposals for looking at different ways to engage with the community so that the energy resilience planning process is not just a process where the utility is understanding what their load base is and being able to provide resilience and reduce the outage time or reduce the percentage of load lost. But we want to be able to bring government stakeholders as well as nonprofits and local community organizers together so that they can better understand what some of those more impacted communities are, what their needs are, so that we can coordinate those efforts together. Another area is looking at different ways to provide rapid energy restoration. So looking at the system as a whole, how can we more quickly model the system, determine where faults are, isolate those faults, and rapidly restore utilizing black start technology within inverter-based resources or small-scale traditional generation to bring the grid back up as quick as possible. And then the third topic that we have for that is around hardening of PV assets themselves, so that during a high wind event, being able to understand what's going on within a solar installation to be able to even reorganize how it's connected within just the panels and strings themselves, so that instead of losing an entire asset, let's be able to bring up as much of the power from it as we can in let's say, a degraded state until trucks can roll and repair that so that it can be utilized to bring the community back up. And with that, I want to say thank you for listening. If you're interested in hearing more about what our office does, please sign up for our newsletter. We'd like to keep engaged with our community and get some feedback from you. So with that, see if there's any questions.
Great, thank you so much, David, for the presentation, and thank you. It was extremely interesting, and I think we have enough time for a couple of questions. I would like to invite people in the audience. If you have any questions, please feel free to raise your hand, and we can hand you a microphone. Okay, we have the first question. So I might need to repeat the question here, but let's see if David can hear it correctly.
Can you hear me?
I can hear you.
Okay, perfect.
Thank you. This is the first time I've heard of grid forming inverters, and I'm familiar with the IEEE 1547 2018 version, which allows inverters to be more compatible with the needs of the grid. I wonder if you could describe for me a little bit more in more detail the difference between an IEEE 1547 2018 compliant inverter and a grid forming inverter.
Yeah, so the real quick and dirty on that really is the IEEE 1547 inverter is what's also called a grid following inverter. It's a current source. So there's a phased lock loop that senses what the frequency on the grid is and injects current during as the sine wave goes, so that 60 hertz cycle. It does not generate that frequency on its own, it's just injecting current. So if the current source, or if that frequency drops away from the traditional generator falling away, the inverter, as per 1547, it will basically go into a momentary cessation. So it will stop injecting current to make sure that it's not like hurting a lineman that's working down the line. A grid forming inverter, on the other hand, though, is what's known as a voltage source. So it will be providing that frequency on its own. And this consortium is also working on new standards so that we can better utilize those types of inverters together and on the grid, so that there's more understanding of the protection needs for them, as well as interconnections between them, so that if that large-scale generation goes out, we can now utilize those grid-forming inverters to provide that frequency support, to provide energy to the grid and that signal to the grid following, so we can continue using all of those inverter-based resources. So it's just a little bit different way of controlling them, and understanding that now that we're shifting some of the more of the generation to the distribution side, we need to be able to better provide frequency support, as well as understanding the protection aspects of it. Does that answer your question?
Okay, yeah, it did. Thank you so much. Do we have any other questions from the audience here? Mm-hmm. If not, there is a question in the Q&A. I'm going to read them for the entire audience. So the first question is, how is the resilience quantification was done on slide 11?
That's a good. I thought that was listed there, but one of the things that we've done some research in the past, and part of this RACER funding opportunity that I mentioned, I neglected to point out that we're also looking at how do we better integrate metrics to understand the resilience of the system and of the community. So moving beyond the safety and SETO metrics that are used for reliability, being able to better understand what the needs are of a community, what the needs for restoration are for the grid as a whole, and developing new metrics where needed so that we can better measure the baseline resilience of a system, and then throughout an event, using those metrics to understand where the system is at and what actions need to be taken.
Okay, great. Thank you so much. And we have one last question also from unless there is anyone else that want to ask any question. If not, we have one last question from the virtual attendee. So the question is, when there are multiple grid forming inverters, who defines frequency and how to stabilize it?
So that is definitely one of the major points of this grid forming consortium. There are some grid forming control algorithms that basically they mimic they're like a virtual oscillator. They mimic what the traditional generation does. So they operate on a droop control. There are some other systems that are more in microgrids, but that do have like have a master and a slave. So one inverter is making the decision, but that requires communication. So we're definitely part of this consortium looking at different ways for us to develop those controls so that they can operate without communications, as well as basically not stepping on each other and sharing the loads appropriately. So more to come on that.
Okay. Thank you so much, David. We'd like to thank again our speaker.